Okay, class, back to bonding. We've discussed VSEPR theory, which helps us understand the overall shapes of molecules. Then we talked about how we have to count electron pairs or structural pairs in order to determine which of these shapes applies to a particular molecule. And we talked about the overall polarity of molecules and whether they had a permanent dipole moment or not. And we talked about some subtleties of bond angles. But now let's get back to what may be a nagging question if you've thought about this deeply. We learned previously that there are atomic orbitals. There are s orbitals, there are p orbitals, and there are d orbitals. And one thing that we realized is that, especially when we go to the p's and the d orbitals, that these are directional, that they align along the Cartesian coordinates, xyz coordinates. And the xyz Cartesian coordinates are based on geometries of 90 degrees. So how do we get bond angles of 120 degrees for trigonal planar? How do we get 109.5 for tetrahedral? How do we get to 120 for trigonal bipyramidal? Well, this was somewhat of a conundrum, but again we turn to Linus Pauling, and he provided an explanation, what is called the valence bond theory. In this valence bond theory, Pauling proposed that the orbitals used in making bonds are no longer the pure atomic orbitals, but they're now molecular orbitals. The basic concept is now, instead of having a single positively charged center at the nucleus where the electrons go around, now you have two positively charged centers nearby, and the paths taken by the electrons will necessarily be different. It's somewhat like a binary star system, where when you have two stars, A and B in this drawing, the planet, instead of going just around A or just around B, will now have to orbit around both A and B. And of course, the example you're probably most familiar with is the planet Tatooine, which orbits around a binary star. You can see the two stars. They are Tatoo 1 and Tatoo 2. Okay, let's get a little more serious about valence bond theory. If you have two electron pairs, we've said that the geometry is a linear geometry. And we will learn shortly that the orbitals that are used are no longer s's and p's, but are some hybridized set of orbitals called sp orbitals. And we'll see that we call them sp orbitals because it takes one s and one p and hybridizes them in a certain way that we will show. If the number of electron pairs is 3, such that the geometry is trigonal planar, instead of using pure s's and 2p orbitals, we use a hybridized orbital set called sp2 hybrid orbitals. And again, we'll see what they look like in a second. If there are 4 electron pairs, the geometry is tetrahedral. The hybrid orbital set that we use is something we call sp3. 1 s and 3 p's hybridized together to form orbitals that now have different shapes. If there are 5, trigonal bipyramidal. And the hybrid orbital set is something we call sp3d. And if there are 6 electron pairs, the octahedral geometry, the hybrid orbital set is something we call sp3d2. In this table, some examples are given of molecules that follow this type of hybridization to form these geometries. Now let's take these one at a time to make sure that we understand. Let's begin with the sp3 hybrid orbitals. So when we say sp3, we mean that somewhere they must have started with one s orbital and 3 p orbitals. So I've shown here what an s orbital would look like and what px, py, and pz would look like. These, of course, must be at energy level 2. And according to Pauling, these hybridize to form orbitals that now have different shapes in different directions. You see in this drawing all 4 sp3 hybrid orbitals, what they look like, and the bond angle between them. Shown a little to the right is what a standard p orbital looks like, and then what an sp3 hybrid orbital would look like, where it's a little bit more elongated on one side. That's the side that's going to approach the other positive center, and the electrons then will spend more of their time in between the two positively charged centers. Okay, a way that we represent this graphically is shown at the bottom of this slide, where I show an energy diagram showing the electron configuration of a carbon atom, where these are the unhybridized or the normal atomic orbitals, where we would place 2 electrons in 2s and place 2 more electrons in any of the 2p orbitals. And when we say hybridized, we mean that you essentially loop together these possible orbitals and make 4 new orbitals now that are all of the same energy level, what we call degenerate, all of the same energy level, and we take the 4 electrons that carbon has or was born with, and we distribute those 4 electrons, one to each of these sp3 hybrid orbitals. And if you look straight above, you'd see the directions and the shapes of these 4 sp3 hybrid orbitals. Now, each of these sp3 hybrid orbitals with 1 electron in an orbital is now ready to form a sigma bond with another atom that approaches it. I sometimes call these sigma bond ready hybrid orbitals. Again, to be more specific, let's talk about methane. When we drew the Lewis structure for methane, we put carbon in the middle, 4 hydrogens. We then talked about VSEPR theory and electron pairs and realized that its shape would be tetrahedral. Well, again, how does it become tetrahedral? Well, because carbon hybridizes and no longer uses its s and p orbitals to form the bonds, but uses sp3 hybrid orbitals. So again, repeating what we had on the previous slide, the 2s and 2p hybrid orbitals for carbon if it were by itself, hybridize in order to form these bonds to form sp3 hybrid orbitals, distributing 1 electron to each, with each of these orbitals now being equal in energy and oriented in the 4 different directions that make up a tetrahedron. So this is then ready to form 4 sigma bonds to 4 hydrogen atoms as they approach. Now, I also showed an alternative representation, which we had in the previous slide, so that you can compare and understand the different ways that we may represent this hybridization process. So in the bottom depiction, I again show the unhybridized carbon with 2 electrons in the 2s energy level and 2 electrons in the 2p energy level, and how this hybridizes to form 4 sp3 hybrid orbitals, which are now intermediate in energy between the 2s and the 2p for the unhybridized case. Okay, so we've just described sp3 hybridization using the example of methane. Now let's go to sp hybrid orbitals. As the name implies, these are hybrid orbitals made from an s orbital plus 2p orbitals. And if these hybridize together, they form hybridized molecular orbitals that now have different shapes and different orientations. They're no longer aligning exactly along the x and the y and z direction, and no longer look like that s orbital. The sp2 hybrid orbitals also have an elongated lobe in one direction, and when you have 3 of them, it forms a trigonal planar geometry as shown. Sketching this out in terms of energy levels, as we did in the previous slide, again I show what unhybridized orbitals would look like for s and p, and then for sp2 we essentially lasso or loop in the 2s orbital and 2 2p orbitals to form 3 hybridized sp2 hybrid orbitals. Now, if you're counting, you realize that we had 1 p orbital that was not involved, did not play in this hybridization game. That we still draw as being a left behind, unhybridized, pure p orbital, which may or may not contain electrons. And we'll see in the next slide that the sp2 hybrid orbitals are sigma bond ready. That is, if we have a single electron in each of these, they can form sigma bonds. And the unhybridized p orbitals may contain 0, 1, or 2 electrons. If a leftover pure p unhybridized p orbital contains only a single electron, we'll see in a second that it is ready to form a pi bond, the second type of bond which we are now getting to. So let's consider formaldehyde. The Lewis dot structure of formaldehyde is shown. The central carbon atom has 3 electron pairs, 3 sigma bonds. We don't count the pi bonds, remember, when we're counting electron pairs. So its basic geometry must be trigonal planar. Now, what hybrid orbital set do we need to have in order to produce a trigonal planar geometry? From that previous table, it was sp2. Okay, so if carbon is going to be the central atom, then let's start with the electron configuration of carbon before it was hybridized, and I show that here. 2 electrons in 2s, 2 electrons in 2p, and then have it hybridize to form a set of sp2 hybrid orbitals. And if we then have 4 electrons, we can distribute these electrons into the sp2 hybrid orbitals and find that we have one additional electron, and we put it in the unhybridized leftover pure p orbital. Okay, and as we said before, the single electrons in each of the sp2 hybrid orbitals are sigma bond ready. They can form sigma bonds to other atoms. In the case of formaldehyde, they form sigma bonds to 2 hydrogen atoms and to 1 oxygen atom. But also, there's an electron in that leftover unhybridized pure p orbital. It is now ready to form a pi bond with another atom that also has a single electron in a p orbital. And that happens to be the case for oxygen. We could draw out the electron configuration of the oxygen, but we will generally focus just on the central atom. So what does this look like? What does a pi bond look like? Well, sigma bonds are directional bonds. They're the type that we think that we understand, where the two atoms come together and the electrons spend most of their time in between the two positively charged centers. Well, what's a pi bond? A pi bond is a type of molecular orbital in which the electrons spend their time above and below the directional sigma bond. This is shown in red in this drawing, and we imagine the two electrons of a pi bond swim around the sigma bond above and below, forming what we call a pi bond. Important consequences of pi bonds are that they strengthen the bond, make it much more difficult to break the bond. They also shorten the bond, and we will see that it prevents that bond from rotating. It essentially locks it in so that the two carbon atoms cannot rotate with respect to each other. Whereas if you have a carbon-carbon single bond or sigma bond, there is free rotation around that sigma bond. And that will become important in organic chemistry. A little bit closer look at what a pi bond looks like. Here, if you imagine having a single electron in each of two p orbitals in two different atoms, essentially we're talking about half-filled p orbitals, leftover unhybridized pure p orbitals, and you can see the little arrows, so there's one electron in each. In a pi bond, those two electrons pair up and form this new funky-looking kind of orbital that goes above and below the directional carbon-carbon sigma bond. Below, I've drawn a sigma bond and how it might be formed from either p orbitals or sp2, sp3, or sp1 hybrid orbitals. Now, how about sp hybridization? Sp hybridization, as the name implies, is hybridization involving an s orbital and one p orbital, forming what we call sp hybrid orbitals. Here I show the individual sp hybrid orbitals, and if you align them together around the same nucleus, it would look like a figure 8 with the nucleus of the hybridized atom right in the middle. Sketching this out in terms of energy diagram shown at the bottom of this slide, we would lasso a 2s and a 2p orbital together to form an sp hybrid orbital set of intermediate energy between the s's and the p's, and here we would have two leftover unhybridized pure p orbitals. And again, the hybridized sp orbitals, if they have a single electron in each, are sigma bond ready to form sigma bonds, and the unhybridized p orbitals may be a source of forming pi bonds. Again, an example is acetylene. I show the Lewis structure for acetylene. It's a linear molecule. So let's see, to be a linear molecule, the central atom, and here we have two central atoms because each carbon has to be viewed as a central atom. But the central atoms must be sp hybridized to form a linear geometry. Okay, so we know they have to be sp hybridized. Well, carbon, the electron configuration of a carbon atom is 2s2, 2p2, as shown here. It must hybridize to form an sp hybrid orbital set, and it would then have left over two p orbitals. If we distribute these electrons, putting one in each, we would have one electron in each of the hybridized sp orbitals and one electron in each of the leftover unhybridized pure p orbitals. That would mean that each carbon then would be sigma bond ready to form two sigma bonds and would potentially be able to form two pi bonds. And that's what happens in acetylene. Each of the carbons can form a sigma bond to a hydrogen and to the other carbon, and can form two pi bonds using these half electron filled pure p orbitals. A structure of acetylene is shown in the bottom left of this slide. And you can see that it looks pretty locked in, pretty complicated with a triple bond. And you can see that there are two red pi orbitals and in addition to the sigma bond that's in blue that's sort of tucked in between these two pi bonds. That's what we think a triple bond looks like. Similarly, I know this may seem like it's getting overwhelming now, but similarly, we can form sp3d hybrid orbitals by hybridizing together an s orbital, 3 p's, and one of the d orbitals. This would only occur at energy level 3 and above, of course, because you only get d orbitals at energy level 3. So we could hybridize together a 3s with 3 of the 3 p's and 1 of the 3 d's to form sp3d hybrid orbitals. That would be 5 equal energy orbitals which have a shape of trigonal bipyramidal. Also, we could hybridize to form sp3d2 hybrid orbitals by hybridizing one 3s with 3 3p's and 2 3d's as shown in the bottom left, lassoing these together to form 6 equal energy sp3d2 hybrid orbitals. We may then have leftover unhybridized d orbitals that we may do something with. But this is how you can form an sp3 hybrid orbital set. Let's summarize this. It may look complicated, but it's easier than it looks. You always begin by drawing the Lewis dot structure. And then you use VSEPR theory and you count the number of electron pairs, electron structural pairs, to determine the molecular geometry, whether it's going to be linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. Then you select the hybrid orbital set that must have been used by the central atom to form that geometry. If that geometry around the central atom is linear, it must have been sp hybrid orbital set. If it's trigonal planar, it must have been sp2. If it's tetrahedral, it must have been sp3, etc., etc., till you get to octahedral. If it's an octahedral geometry around the central atom, it must have been sp3d2. And then you sketch things out. And in some cases, you may have to place non-bonded pairs in the least crowded positions, and you may have to accommodate pi bonds. But you try some, and you'll see that it works. Okay, we'll stop now, and then we'll move on to what is called molecular orbital theory. Tattoo 1 and Tattoo 2. Bet you didn't know that that was the name of those stars.